Schwartz who asked me. He was like,
okay, good. Sorry about the many delays. Anyone watching at home, we had some problem with like batteries and other crap, so we got cut off. We did the proof without you. There it is. Hit pause. Read it carefully. Let's move on. All right. There's homework. And let's try to do some of these problems. I thought there were two in particular that were really difficult. 1B was just do it, right? That was. Do we need to talk about that? No. 17. Prove. I didn't even do this one. 17 says if c to the 5th plus 7 is even, then c is odd. I think this is pretty easy, right? To prove that, so we assume c to the 5th plus 7 is even. I want to prove that c is odd. So suppose c is even. Well, that's going to be a contradiction, because if c is even, then by properties of multiplying even numbers, c to the 5th is also even, but then c to the 5th plus 7 would be odd, and that would be a contradiction. Good? Yep. Okay, good. Done. Next, 21. 21, I thought was very tricky.
yeah. I know, I like.
Okay. I think we need like a whole board for this. I did this last year, and I couldn't believe how hard it was. And I think I was shocked that my proof was so convoluted, and then Eric Neiman was like, "Yep, that's actually what you have to do." Right there, if you got 21.
Possibly, not sure.
1, 2.5 persons.
Oh yeah. I just wrote things. I just wrote everything in sentences.
All right. So this is the best I can do, and I think it just is the best. So number 21.
I know what I'm doing.
First off, let A, B, C be Pythagorean triples. Primitive Pythagorean triples. It's really important. Primitive Pythagorean. Cool. Yeah. A is odd, and A is odd. A is odd, and by the way, if you don't know what primitive Pythagorean triple is, it means that A squared plus B squared equals C squared, and A, B, and C do not have a factor in common. Besides 1. They're in the lowest terms. Okay. Here is what we have to. Oh, and then they mentioned, hey, now, if A squared plus B squared equals C squared, we can write A squared as C squared minus B squared, and we can write that as the difference of squares. Okay, now the problem begins. It says, use a proof by contradiction to show that C plus B and C minus B have no common prime factors. All right, let's do it. Show, this is part A, show that C minus B, C plus B have no common prime factors. All right. Well, here is what I came up with. I'm going to do it by contradiction. Straight opposing. Okay, so let's suppose that they do have a common prime factor and try to get a contradiction. Okay, so suppose that we have prime P. Suppose we have prime P. What do you do? Suppose we have prime P where P divides C minus B and P divides C plus B. And let's see if this leads to a contradiction. Well, I said if this is the case that that P is a prime factor, or that we have prime factor P of these two things, then we can write C plus B as P times some number like n. And we can write C minus B as P times some number like m. And now, what? Yeah. Now I'm tempted to add these equations. That seems like a good idea. If we add these, did anyone else do something like this?
Yeah, so you can just say that
Eo did.
Oh, yeah.
P divides 2A.
So-
and then
Oh,
the
that's-
difference.
Say it again.
You can just say that P divides the sum and the difference.
P divides the sum and the difference, true.
And then
Same thing. Okay, so when we add these up, we get 2C equals P times M plus N. Right, and now there are some careful kind of parity arguments I can make about N and M themselves. Let's see, where does this come from?
A is odd.
A is odd, yeah. So I'm going to do this kind of off to the side, but this is important. Important facts. A is odd. Since A is odd, A squared is odd. Since A squared is odd, if A squared has two factors, they must both be odd. Okay, so that's just a whole bunch of inferences, right? A is odd without giving all the details. Since A is odd, A squared is odd, and therefore, if A squared can be factored as two things, those two factors must be odd. So I know that C plus B is odd, and I also know that C minus B is odd. Why is that worth talking about? Well, I think, since this is odd, P and M and P and M must also be odd by the same exact argument, right? So again, from this I conclude that A being odd means that A squared is odd, means that A's factors are odd, means that the factors of each of these two are odd. So I claim that P, N, and M are odd. Jason, follow? Alright, that is required now because what I really want to do is like divide by 2, and I want to make sure that that's going to be an integer and everything, right? So if N and M are odd, then M plus N is even. So C can be written as P times M plus N over 2. I'm kind of too lazy to write it because the board's getting really full. But no, if I know you're with me, this is an integer, right? Because N and M are odd, so N plus M is even, so when I divide by 2, it's still an integer. Thus, I have now proven,
How do you get that M plus M? Oh,
because N and M are odd,
how do you get 2C?
I added these two
Right,
equations.
right, right.
I added these two equations. So from this, I conclude that P divides C. Well, similarly, I can do the same thing again, right? C plus B equals P times N, C minus B equals P times M. By the exact same logic, now I could subtract the two equations. I get that 2B equals P n minus M. Again, since N and M are odd, their difference is even. So when I divide by 2, I get an integer. So I have expressed B as P times an integer, so P divides B. Alright, so I mean, I'm headed towards a contradiction. If you think about it, what's the only possible contradiction that there is to get? That they're not primitive, right? I begin with, just to recap, I begin with A, B, and C as primitive Pythagorean triples. So I know that they have this relationship, I'm supposing what I know to be false, that P is a factor of these two guys, and the contradiction I'm going to get is with the primitiveness. So that's why I tried to show that P. So I've showed that P is a factor of C. I've showed that P is a factor of B. If I can prove that P is a factor of A, then I have my contradiction. Because now I've showed that A, B, and C all have a factor of P, and hence it's not primitive. Are you guys with me? Okay, good. How do I show that P is a factor of A? Well, this is the only way I could think of to do it. I said, take A squared. A squared is, of course, C minus B times C plus B. But let's now write it in our new form as Pn Pm. So A squared can be written as Pn times Pm. Well, that can be written as A squared equals P times Pnm. And I think I'm done, right? Oh, am I done?
No,
Yeah.
No, you
No,
just
you have
square
square
root.
root.
Yeah.
Yeah, you need to.
Oh,
P
right.
squared, so-
No, I remember now.
Yeah.
So P divides A squared. So why must P divide hold on.
Take this and show like.
Yeah. Wait, hold on. I lost the logic for a second though. A squared is p times.
Or it has to be
Right. Oh. Wait. Say it again, Ethan.
Because the thing, we know that p divides a squared, right? And p is a prime.
Oh, yeah. Oh, right, of course, duh. So a squared can be written like this, so we conclude that p divides a squared. But what I actually wanted was that p divides a. But now I apply the prime divisibility property. Apply the prime divisibility property that we did at the beginning and just erased. The prime divisibility property says that if a prime divides the product of two numbers, it must divide the two numbers. But since those two numbers are the same, then P must divide A. Whew, that was really hard. If P divides A, B, and C, then A, B, and C are not primitive. Then A, B, and C not primitive, and that is a contradiction. Okay, yo, was this what you did?
Yeah, sort of.
Like, close?
I square rooted at the end, but
Otherwise the same, yeah. Well. Did anyone do anything different? I think last year we concluded there was almost nothing else to do. Yeah.
I did something kind of different, but I don't know if mine is okay or not.
Okay, let's move on.
Basically, I found that A can be represented as 2 times something, 2 times k, and that's bad. I did contradiction again. So instead of showing contradiction with the primitive, I showed a contradiction with the oddness.
With the oddness. Okay.
So I don't know if that's.
I don't know. Alright, it's probably, maybe works. Okay. Alright, half done with this proof. We're going to use part A and part B. Part B says, now, this is the real deal, show that they're both squares. So, part B says, prove that C plus B and C minus B are squares. Okay. Are perfect squares.
Yay.
Well, here was my only way I could think of to show that something was a perfect square. I supposed that I took the first one. I'm going to show that this is a perfect square, right? So show C plus B is a perfect square. Well, I claim that it's sufficient to take a prime factor of C plus B and to show that if a prime factor divides C plus B, then so does its square. That was my strategy. I said, I mean, you might object to this, but I think this is sufficient. Suppose that P divides C plus B for prime P, and I'm going to conclude that P squared also divides C plus B. In other words, for any prime, if it divides C plus B, so does its square. And so, perhaps the full fundamental theorem of arithmetic is required, but I think that if I can show any prime factor exists in 2 copies, then that's sufficient to show that it's a perfect square. EO buys it. Anyone else? Yeah. Okay. So how? Why is that sufficient? Because I mean, take a number like suppose prime number 3 is a factor of this number.
Okay.
Well, if on the assumption that 3 is a factor, if 9 is also a factor. Yeah, shit. I think that works because maybe P can't be a prime.
Yeah.
Alright. If any number is a factor, that would be just false.
Yeah.
Like,
What's this show? P squared equals C plus B.
oh man, really? Interesting.
Yeah.
Gabe,
Other ways.
you have a better way to do this?
I don't know, maybe not.
Okay.
But like, since it's equal to a squared, the square root of them multiplied together has to be, like them,
when they're multiplied together, they're a perfect square. That doesn't prove that each of them is a perfect square, but you just proved that they don't have any like things in common.
Yeah.
I didn't follow that.
Like,
Someone
they don't,
say.
we just proved that they
Sage.
don't have any.
So like, basically just write out a squared equals c minus b times c plus b.
Okay.
You can square root both sides and separate the square root.
So a squared equals c squared minus b squared equals c minus b times c plus b. Okay. Say it again.
Square root both sides, so you get like a equals like c minus b. And you can separate the two, and you also know that they have no common factors, so they both have to be like perfect squares. Yeah.
Oh, that's, yeah.
That makes sense.
Just take a square root.
Yeah.
And A has to be.
You take a square root.
Yes,
Okay,
that's true.
so take the square root
So
and
then you
so
have the
what?
square root of c minus b and times the square root of c plus b.
Yeah.
And you know that none of them have common prime factors. So they have
So-
I don't think you need to separate
Right?
the square root. I think you can say
Yeah.
because they have no factors in common, you can say that those two multiplied together have to equal some like a prime. Right?
Yeah.
So, like,
So I think maybe I kind of do need to use the fundamental root here. I think I really sort of do, right? You can just say A has two. A is a product of a bunch of primes. I'm just trying to find a way to say it correctly. A
is the product of a bunch of primes. A
Yeah.
squared is the product of squares of primes.
Yeah.
And then c minus b and c plus b don't share any factors.
Yeah.
So all the squares of the
Are
prime
one or
have
the
to be
other.
contained in one or the other.
Yeah. Okay. So yeah. So basically, that's I guess that's what we do, right? We just say, yo, by the fundamental theorem of arithmetic, A is expressible as a product of primes. So like some people do crap like this. They're like, the first prime to how am I doing? To some number like x1 and times the second prime to x2 times the third prime to x3, etc.
Show c plus b square.
Wait, hold on. So in other words, every number is expressible as a product of primes to some power. So if that's what A looks like, then A squared has to be a bunch of primes to like even powers. So this is like P1 2x1, P2 2x2, P3 2x3, and then each of these must for each of these primes, as c minus b and c plus b have no prime factors in common, they have to all either live in one or the other. Is that good enough? I feel like that's good enough. That's pretty much what you're saying, right? Yeah. So for each pi, in other words, for each prime, since c minus b and c plus b have no common prime factors, then it lives all in that one or all in that one. Is this good, Ari? Is there a cleaner way to do this, or?
It was kind of sketchy.
Same thing.
Yeah.
This is yeah. I'm trying to make it precise, but it's like too much effort to make it really precise. But basically, yeah. Each of these. I have an even number of prime factors of p, and they have to either be here or here, and thus c minus b and c plus b have all even powers of primes in them, and so they're each perfect squares. I'll take that. Okay, good. Can you write this proof sucks 27 on the bottom so I never remember to do that over next year? All right. Good. I think we have time for like one more.
That was 21.
What?
That was 21.
That was 21. Yeah.
We should do
21.
There were 4 more to talk about, but some of them were like trivial, right?
yeah.
25 was you just do it.
Yeah.
25 was you just do it. 30 was 30 was a little tricky. Should we talk about 30? No, you have to switch the camera. 30 says, let p over q be an integer. rational number. Prove constructively that there exists an integer n. So find n such that p over q is less than n. It's kind of a weird problem. It's like basically like, yo, produce a number n which is guaranteed to be greater than this. I wrote a whole bunch of stuff. It seems like overkill. I don't know. Thoughts from the audience? Yeah, Ramya.
Could you write p as aq plus b? Where a and b are integers?
Write p as that.
Yeah.
Yeah, that's kind of what I did actually.
And then you just do a plus 1 because you know that p over q is less than 1.
Yeah, that's what I did. She says apply the Euclidean division algorithm.
Wait, is it the Euclidean division algorithm?
No. Yes. The first one. Apply the Euclidean division algorithm, which is not an algorithm, but Victoria's not here, so screw her. So apply the Euclidean division algorithm to P. P must be expressible as Q times A plus R, where R is guaranteed to be less than Q. This is how I did it. This is pretty much what you did too? Less than, yeah. In other words, any number can be expressed as some number of Q's plus a remainder with a remainder. And then, am I done yet? Now I just divide. So I have QA plus R over Q is less, well no, I have QA plus R over Q. Yeah. And now what? That's A plus, wait, hold on.
Yeah, it's A plus.
Oh. Sure. That's just,
that number.
this is just A plus R over Q, but now as R is guaranteed to be less than Q, this number is guaranteed to be less than just A plus 1.
Yeah.
And therefore, A plus 1 is such a number.
I have a weird way of doing it.
Okay, hold on, let me just repeat this for emphasis. To find a number, a natural number which is guaranteed to be bigger than P over Q, we start with P over Q, we express the numerator using the Euclidean division algorithm, boom, 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 and then since R is guaranteed to be less than Q, this is less than A plus 1, so A plus 1 will do it. Yes?
I just found a formula for a number that's always bigger than that.
Okay. What is it?
P plus 1 times Q is always larger than
P
P
plus
divided
1
by Q.
times Q. So he says he claims that P plus 1 times Q is guaranteed to be bigger than P over Q.
Yeah.
Why is that true?
Because it is. Because P is less than P plus 1, which is less than or equal to P plus 1 times Q, and P over Q is less than or equal to P, which is less than P plus 1 times Q. So, I mean, it's just a bunch of inequalities that like work out if like
Okay.
P and Q are like not stupid numbers.
Okay, cool. Good. So maybe the answer is yeah. In fact, I skipped the annoying part where it says let everything be positive.
Yeah, everything isn't it in the question that it's positive?
No, it says integers, but that's just busy work. Okay, last one.
You said it was negative.
Wait, what's the run?
Yes.
Q not allowed to be less than 1.
Oh right, we don't even know P Q.
Yeah, P and Q have to be
No, no.
P and Q don't have to be integers, but you can multiply them by something to make them integers.
Yeah, but it's not in like.
What if P equals 2i?
Yeah, technically I said, okay, ready? So here's what I did. If you really want to know what I did, I said, yo, take P over Q. I mean, in the privacy of my own home when I had time and stuff, I said, P over Q. Okay, look, it might be negative. If it's negative, then set n equal to 1. Okay, that gets rid of that stupid negative case. Therefore, maybe they're both negative. Well, if they're both negative, then make them both positive. So now, from now on, we can just assume that P and Q are positive, and then I actually started the proof. Is that you guys put me on that? Yes, Sam.
So if since yours, did it say that P and Q are integers?
It said that P and Q were integers.
It does not say
Well, it
that.
doesn't say that they're integers, but it says that it's a rational number, which implies that they're integers.
Okay, I mean, I did a weird thing with the ceiling function. It doesn't require you to split a P and Q, so I don't know.
Okay, good. All right. Good. Is this helping going over this? Should we do the last one? I don't feel like it. I don't want to do the last one. It's going to take like 15 minutes, and then we'll have no time left for math. Hold on to this homework I'll select it at the very beginning of next class, all together with the people who aren't here, because it is like 10 people. Maybe it's 1, 2, 3, 4, 5, 6, 7 people. Alright, so, who is feeling smart? Christina, are you feeling smarter than you were like a week ago? I am. Good. Josephine, smarter? No? Linda, smarter? Good. That was the point of this section. Alright, now we do a new, powerful, and amazing proof technique that you might have heard of. It is called induction. Deep questions about induction will be ignored because there is a class called Logic Math in which we talk about this deeply.
So I take it we're not doing transfinite induction.
We are not going to be doing transfinite induction. What we are going to do is prove induction. Whoa. And though in logic math and in traditional axiomatizations of the natural numbers, induction is taken as an axiom, the way Gossett does it for whatever reason is to take as the axiom the WOP, the well-ordering principle. And what we will show today, or possibly next class, probably today, that using the WOP we can prove induction. First off, what is induction? Induction is, and you all learned this, probably from me, in Pre-Calc C, or have you ever heard of induction before? Oh man. Well, you all except for Benda learned this in Pre-Calc C or functions? Yes.
Can induction prove the law?
Yes.
Okay.
Yep, good, and we're going to prove all those things. So, what is, and I'm going to call it mathematical induction, and there's this whole, okay, Gossett calls it MI, there's another name for it, I'll tell you later. So mathematical induction simply says, you all have seen this before, it says, if some property holds of the first number, where first can mean 1 or 0 depending on the context, and whenever, let's use eyes, and whenever it is true for a number, it is true for the next number. In other words, if a property holds of a number, and whenever that property is true for a number, it's true for the next number, then, and here's a giant parentheses, it's true for all numbers. Okay, that is probably, I probably wrote something almost exactly like this on the board when you first learned this in Pre-Calc C or functions. And even if you didn't take logic, I think we've seen induction before. Should we do a super fast induction proof just for Benda? Benda, suppose you want to prove some crap about numbers. It's really hard. There's no real way to do it. You just do it by induction. In particular, take the following happy little theorem. It goes like this. If you take the sum of the squares, 1 plus 4 plus 9 plus, all the way up to n squared, it can be shown via interesting, ingenious algebraic and or geometric methods that this is n plus 1 times 2n plus 1 over 6. Okay, so I'd like to prove this. This would be my goal, would be to prove this. How do I prove this? By induction. And what we do is, at least in my world, we temporarily name this expression like a sub 1, and we temporarily name, no, a sub n, and we temporarily name this expression b sub n, just for clarity and ease of reference. And what I would really like to do is show that a sub n and b sub n are the same for any possible number that you might pick. So that it works for n equals 1, it works for n equals 2, it works for n equals 3, etc. Okay, well, let's check it if it's true for n equals 1. Well, when n equals 1, a sub n is just 1, so a sub 1 is just 1, and b sub 1 is 6 over 6, it's also 1, it works, right?
Yeah.
Okay, now, the main thing to do would just be to check it for 2, check it for 3, check it for 4, just quit your job, just sit around all day checking it and making sure it's right. Alright, but I would like to prove that it works for all possible numbers, so instead, I use induction. How? I suppose, temporarily, that the equation holds for some number k. And from this assumption, I'm going to show that a sub k plus 1 equals b sub k plus 1. And if I can do that, then I've shown that whenever the equation holds for a number, it holds for the next number. So since it holds for 1, it must hold for 2. Since it holds for 2, it must hold for 3, etc. Does it make sense?
Yeah.
Yeah, and then this is typically not so hard. It's like an algebra thing, right? I know this is true. I want to show that's true. So I start with a sub k plus 1. A sub k plus 1 is by definition just 1 plus 4 plus all the way up to a sub k plus a sub k plus 1. No, plus what? Plus n squared, no one saw that. Except the internet. Plus
K. Yeah.
no one saw that either. K squared plus k plus 1 squared. And now what we do is we say, well, that is, by our assumption, just that.
Right.
And so this is equal to k plus 1, 2k plus 1, all over 6 plus k plus 1 squared. And if you just algebra that out, you're just going to get you're going to get this with k plus 1 stuck in, I promise it works. Okay. I'm going to stop now. Raise your hand if you haven't done this in like a long... Have you totally forgotten induction? I wonder what Kentia and Angel kind of... Should I finish this off?
Yeah.
I'll finish this off. I ran out of space though. So I guess the thing to do would be to factor out a k plus 1. So if I factor out a k plus 1, I'm left with k, 2k plus 1 plus, I'll call it 6. K, am I doing this right? All over 6. I don't think I messed up yet. Not yet. Okay, so this is k plus 1 over 6 times 2k squared plus k plus 6k plus 6. So that is 2k squared plus 7k plus 6. And hopefully that just factors. Doesn't look right.
2k plus 1. Is that what?
No, but it doesn't.
Well, yeah.
Oh, it does. It does. So this is k plus 1 times k plus 2 times 2k plus 3. Is that right? 2k squared. Yeah.
Yeah.
All over 6.
Oh, so it's just
that
right.
just is.
Right. Yeah.
That just is this. If you want to be a little more picky about it, it's 2k plus 1 plus 1 all over 6.